Okay, so good morning all. Today we will see the next part of a inverter. Uh, just for my confirmation, anyone just unmute yourself and tell me am I audible or not, so that we will proceed. Just anyone?
Yes, sir.
Okay, okay. Thank you. So I'll start the session. Few students are uh, entering for the meeting. So already we have seen single phase inverter, that is half a bridge, single phase half bridge voltage source inverter for R and RL load, right? So for both the loads, already we have seen the single phase half bridge voltage source inverter. I'll just, before to join the students to the meeting, I'll just explain the operation with RL load in short, so that the students, maybe maximum students will join the meeting and then we will see the next part. Okay, so in this particular circuit, if you are using RL load, if the R load is replaced with RL load, so how the circuit will work, that I just explain in a short, and then we will go for the full bridge. Okay, so here the circuit consists of two batteries, two switches, and two diodes. Now in this circuit, diodes are required. Okay, so without diode, this circuit will not work properly. Your current may be discontinuous, so that you require the diodes, right? In a resistive load, these diodes are maybe optional. You can connect here, but the no use of these diodes with resistive load. But with inductive load, these diodes are required. Okay, so we consider that this load is an inductive load, and when S1 is on, S1 is sorry, S1 and S2 both are off. That is the first case. Then no current flow through the load, right? So output is equal to 0. This is the first case when both switches are off. Second case, when switch S1 is on. In the second case, when switch S1 is on, then current start to flow from upper ADC, that is ADC1. You can say, you can give the name ADC1 and ADC2, okay, or ADC1 by 2 and ADC2 by 2. Okay, so this ADC1 is a name. Okay, so current start to flow from ADC1 plus, then P, then S1, then A, then load, and then back O, back to the negative. So current direction is from A to O. Okay, so that time you will get a positive cycle. Here it's a EDC by 2. Output voltage is EDC by 2. We'll start from this T1. Okay, so here yes, T1, at time T1 S1 is on, so your output voltage is positive. Okay, then when S1 is off, okay, what happens when S1 is on? That time this inductive load store the energy with the polarity that is given as a plus here. A is positive with respect to O. Okay, this is the stored charge energy polarity. Okay, the energy stored by inductive load and its polarity is A is positive with respect to O. Okay, this is the first condition. Now when S1 is off, S1 is turned off, what happens? The inductive energy stored by this RL load gets reverse its polarity. So O is positive with respect to A. Okay, O is positive with respect to A. So if A is negative, it means that diode D2 is in forward bias condition, D1 is in reverse bias condition, right? So current start to flow from this positive O, then battery, and then diode D2, then back to A, and then negative of load. Okay. If you see here, the current direction is still same. That is, current direction is still same. So what happens? The output current is still positive. Output current is still positive, but here it is decreasing because the inductive load start to release the energy, so it decreases, and at instant t3 it becomes a zero, right? This is a energy stored by inductor. That inductor release the energy, So that energy releases, it means that the current still positive, but it decreasing. And at instant T3, this current is equal to 0, right? This current equal to 0. Now at time instant T3, S2 is on. S2 is on. This is the third case. Okay. First case when both are off. Second case when S1 is on. Third case when S1 is off. Now it's a fourth case when S2 is on. S2 is on. Then what happens when S2 is on? Then current start to flow through EDC by 2, that is the second battery, then O, then load, then IO, that is A, then S2, and back to the battery. Now this time the current direction is reverse. The polarity, that is voltage, that is stored across inductor, O is positive with respect to A, that is A is negative. The current direction is reverse, so that in output waveforms you can see that at time instant T3 your current start to increase, but in a negative direction. Current increases but in negative direction. Okay, it means your current is negative, and at that instant the voltage is also equal to negative EDC by 2. Okay, when last case when S2 is also off. If S2 off, then what happens? The stored charge polarity of this inductor gets reversed. Now A is positive with respect to O. Okay, then A is positive with respect to O. So if A is positive, it means that diode D1 is in forward bias condition. So current start to flow, that inductor energy releases through this diode D1, then P, then EDC back to the negative of inductive load. So current direction is again the same, right? And so that you can check here in output waveform, the current is still negative, but it in decreases in a negative direction. So maximum negative, then decreases, and again it becomes a 0. So at this instant, again, what happens? The diode D1 is on, right? Diode D1 on, current flows from inductive load to D1, then back to the P, EDC by 2, and then back to the inductive. So these are the total 5 cases. In these output waveform, total 4 cases are explained. This is the first case, but actually it is called as a fourth case. So this is a diode D1 on. That time the output voltage is positive and current is negative. Then S1 is on, output voltage is positive, current is positive. Then next, when D2 is on, output voltage is negative, but current is still positive. And when S2 is on, current is negative, output voltage is also negative. So you can check here, during S1 is on, output voltage is positive, current is also positive. When S2 is on, output voltage is negative and current is also negative. Okay, when diode D1 is on, current negative. When diode D2 is on, current positive. Okay, so this is our output voltage and current. These are the energy stored by inductive load. S1, when S1 is on, that time, when S2 is on, that time, and these are the diode currents. So diode currents, SCR currents, or switch current you can say, and this is the output voltage and output current, load current and load voltage, right? So this is about the operation with RL load. Total there are 4 cases are explained in this particular output waveform, but you can explain total 5 cases. First case, when S1 is off and S2 is off. When both switches are off, no current flow through the inductive load, right? So output voltage also equal to 0. That is your first case. So in examination, you can directly write case 1, when S1 is off, S2 is off. If S1 is off, S2 is off, then no current flow through the load. So output voltage is equal to 0, full stop. Second case, case 2, when S1 is on, when S1 is on, then what happens? The current start to flow from upper battery, then P, then S1, then inductive load, sorry, A point, then inductive load, then O, and then back to the negative terminal of battery. This time, the inductor stores the energy in its magnetic field. The polarity of stored charge is A positive with respect to, sorry, A positive with respect to O, right? Then third case, case number third, when S1 is turns off, when S1 is turns off, then what happens? The inductive energy which is stored maybe across, maybe in a magnetic field of inductor, so its polarity gets reversed. So this time the O is positive with respect to A. When A is negative, it means diode D2 is in forward bias. So current start to flow from inductive energy to the lower battery, lower half battery, then N, then D2, then A, and then again back to the inductor. This time inductor release the energy, but the direction of current is still positive. So current is positive, but it decreasing as shown in a waveforms, right? Then third case, uh, first, second, third. That is when S2 is on. When S2 is on, then current start to flow from lower battery to O, then load, then S2, then N, and back to the negative terminal of battery, right? So this time the inductor store the energy with the polarity O positive and A negative, right? So whenever the S2 turns off, then again the polarity of stored charge get reversed. Now A is positive with respect to O. If A is positive, diode D1 is in forward bias condition. So inductor start to release the energy through uh, point A, then diode D1, then point uh, P, then positive terminal of battery, negative terminal of battery, and back to the O, and then negative terminal of stored charge, right? So as shown in figure, this time the current direction is still negative, right? But output voltage is positive. So this is a working in a 5 cases. You can explain in a proper way so that you will get a maximum mark. So draw the diagram, uh, that is circuit diagram. Then these notations are important, P, N, O, A, so that you can explain properly. Then you can draw these waveforms, right? And then the equations. See, this is actually operating modes. What I explain you, I have explained you total 5 modes. That is the first mode that is not shown here when S1, S2 both are off. But in this particular diagram, when S1 is on, current direction, voltage is positive, current direction is shown. Then case number 2, when inductive energy releases through lower ADC by 2, diode D2, so that time the current direction is shown here, right? Then output voltage is also given. Then third case and then fourth case, right? So operating modes are given for your reference. Total theory explained here in a proper way, so we can read it properly. Mode 1, mode 2, or you can say case 1, case 2, case 3, and case 4. Okay. One additional case I explain you, because when S1 and S2 both are off, that time no current flow, so output voltage is equal to 0. This is the additional case I explained. Okay. So this is about the single phase half bridge voltage source inverter. Now, single phase full bridge inverter for R load and for RL load, right? So we will see first R load. In this particular diagram, you can see here total 4 switches, S1, S2, S3, S4. Here you can give the notations in the same way, okay? Because the on time, maybe a switch S1 and S2 is on at a time, and S3 and S4 is on at a time. So cross one switch from upper arm and second switch from lower arm should be turns on at the same time. Okay, the same switches in the same arm should not be turns on, right? S1 and S4 should not turns on at a time. Otherwise, no current flow through the load. Keep in mind, this is the S1. Okay, this is the S1. I don't know you have maybe seen properly or not, but this switch is called S1. Okay, this is S2. This switch is S4. So if the same switch or maybe switches in the same arm, if turns on, then no current flow through the load. Your current flows through only this particular loop, right? So the switches from the same arm should not be turns on at the same time. Okay, so when S1 is on and S2 is on, that time your current flow through the circuit or load, right? So S1, S2, S3, S4, you can give the name in the same way so that you can explain in a proper way. Okay, So S1 and cross S2, upper S3 and cross S4. Okay, it is very simple because when S1 is on, that time this switch that is called S4 or switch in the same arm should not be turned on. So remaining switch is this one. So this switch is and this switch. Both switches are on at a time and remaining S3 and S4 is on at a time. Okay, so you should give the proper notations. These are very important. Otherwise, while explaining, you may have maybe some difficulty or your explanation may be wrong, right? So give the proper name. Even similarly, D1, D2, D3, and D4. So same kind of names are given. Again, two diodes are turns on at a time. Okay, so that we will see for inductive load, but for resistive load there is no use of diode D1, D2, D3 and D4. Keep in mind, for resistive load, if you draw these diodes or maybe if you not draw, no problem, your circuit will work properly. Okay, but in this particular PPT, the same circuit I have used for resistive load and for inductive load, and that's why I have drawn the same circuit. Even you can check in any book, you will find that the same circuit is used for resistive load and same circuit used for inductive load. So with resistive load, diode D1, D2, D3, D4s are not used, but still they are connected in the circuit. Okay, so there is no harm to connect the diode in a circuit with resistive load, but with inductive load these diodes are required. Okay, so there are total four switches. This forms a bridge, S1, S2, S3, S4. So this forms a proper bridge, right? And you can have maybe a load, that is resistive load, right? So again I want to clear one thing. These S1, S2, S3, S4 are the power switches like power BJT, power MOSFET, IGBT, SCR, JTO, etc. So these switches require a triggering circuit and protection circuits. For simplicity, the triggering circuit and protection circuit is not shown in a figure. Okay, but this should be very important. So keep in your mind the circuit requires triggering circuit. Sorry, these switches require triggering circuit as well as protection circuits. Okay, but protection circuit and triggering circuit is not shown here for simplicity. So it is required. Okay, so we will start with the first one, that is a resistive load, right? So in a resistive load, total four switches and four diodes are used, but diode is not used actually in a circuit. So we can consider only four switches. So first case, when all the switches are off, that time the current flow through the load is equal to zero. Even if S1 is and S4 is on, no current flow through the load. And if S3 and S2 is on at a time, no current flow through the load, right? So it should be conducted in a cross only. When S1 is on, S2 should be on. So same triggering circuit is used for S1 and S2 and same triggering circuit for S3 and S4. Okay, so that the S1 and S2 turns on at the same time. Similarly, S3 and S4 turns on at similar time, right? So keep in mind the triggering circuit for S1 and S2 is the same. Triggering circuit for S3 and S4 is also same, so that the triggering pulses are applied to these switches at the same time. Okay, so we'll start with the first case. All switches are off, no current. Then second case, when S1 is on and S2 is on, because the same trigger circuit is used. So when S1 is on, automatically S2 is also is in on state. Why? Because the same triggering circuit is used for S1 and S2. Now, then current start to flow. Again, the battery notation given in a circuit diagram is wrong. So upper terminal is positive, lower is negative, right? So current start to flow from positive of a battery, then S1, then P, P is a notation, then a load, then Q, then S2, and then back to the negative terminal of battery. Okay, so current direction is P to Q. P is positive with respect to Q. Okay, P is positive with respect to Q. So this time the current is positive and your output voltage is also positive. Voltage is equal to EDC. See, this is the first part, right? So during this particular time, your S1 is on, S2 is on, mode 1. See here at the bottom of this output waveform, S1, S2 is on, okay? So that time the voltage is positive and current is also equal to positive for resistive load, right? Up to time T by 2, up to time T by 2. At T by 2, this S1 and S2 both turns off, okay? See, it's a resistive load, so no energy stored across the resistive load. So during when S1 and S2 is on, that time the voltage, or sorry, current start to flow from positive terminal of battery to the S1, then P, then a load, then Q, S2, and then back to the negative terminal of battery. This time the voltage across the load, that is P, is positive with respect to Q. So we can consider the output voltage is positive as well as output current is also equal to positive. The current is equal to ADC by R, and this is up to the T by 2. Okay. At T by 2, the S1 and S2 both turns off. S1 and S2 both turns off. At the same time, the S3 and S4 turns on. At the same time, when S1 and S2 is off, then S3 and S4 must be turns on. We required here, if you are using BJT, MOSFET, IGBT, any other device, simply remove the gate bias, your switches turns off, right? And just apply triggering pulse to the S3 and S4, they should be turns on. But if you are using SCR, then it is quite difficult because S1 is never turns on simply by removing gate bias. So you require a force commutation so that slowly you remove the current, gate current up to the or less than the holding current, then S1 turns off. Similarly, remove the gate current less than holding current, then S2 turns off, and then after that apply triggering pulse to the S3 and S4. So with SCR, it is quite difficult because you required a force triggering circuit, right? But for simple IGBT, MOSFET, or BJT, you required simply remove the gate current from S1 and S2. Automatically S1, S2 turns off. At the same time, you can apply gate pulse to the S3 and S4. Okay. So when you apply gate pulse to the S3 and S4, what happens, that we will see. Okay. So if you apply gate pulse to the S3 and S4, current start to flow from ADC by, sorry, plus ADC by 2, sorry, ADC, then S3, then Q, then load, then P, then S4, and then back to the negative terminal of battery. You can check here, the current direction is reverse. This time the voltage across load Q is positive with respect to P, right? So current direction is negative. You can check here, minus ADC by R, and this time the voltage is also negative, that is minus ADC. Voltage across load is minus ADC. Okay, so current flows from plus ADC to S3 to the Q, then load, then P, then S4, and then back to the negative terminal of ADC. So current direction is reverse. Current flows from Q to P, so that current is negative and voltage developed across this resistive load, that is your output voltage, is also negative. You can check here at the bottom of this output waveform, when S3 and S4 is on, this time the output voltage is negative, current is also negative. These are the gate pulses for S1, S2, then S1, S2, and this is for S3, S4 and S3, S4. So these are the gate pulses are shown here. When S1, S2 is on, that time the output voltage is positive, current is positive. Okay, and when S3 and S4 is on, that time output voltage is negative and current is also negative. Okay, so this is the working of this single phase full bridge voltage source inverter. Okay, Any doubt in this particular circuit or working, you can ask me. Only two modes of operation, mode 1 and mode 2. Additional, that is when S1, S2, S3, S4 is on, that time no current and no voltage will develop across the load, so output voltage is equal to 0. That is the case first. Okay, and this is a case 2, you can say, or mode 1 and mode 2. In mode 1 or case 1, S1, S2 is on, and in case 2, S3, S4 is on. Okay, so no use of diode D1, D2, D3, D4 with a resistive load. See here the operation with the waveforms that is shown here. S1 is on, current flow from P to Q, S2 is on, and then the output current, that is output voltage, is positive and current is also positive. And in a second mode, current flows from plus ADC S3, then load S4 back to the negative terminal of battery. Okay, then that is also shown here, mode 1 and mode 2. So total working for your reference. Now this time the RMS output voltage equal to EDC. With a half bridge, it is ADC by 2 or equal to supply voltage. So here directly given as the ADC, you can find out the output RMS voltage with the help of these equations that is given here, right? EO average equal to 1 upon pi pi integration 0 to 2 pi E 0 omega t d omega t. So put the value of this particular into this equation that is called EO RMS. Okay, so you will get here the output EO RMS equal to EDC by 2. So same you will get only EDC with a full bridge, right? So with full bridge, single phase full bridge, you will get EDC by 2, sorry, only EDC. Then in Fourier series, the same thing for AN equal to 0 for all the even and odd values. BN is also equal to 0 for all even values. So you can find out with the help of this equation. So you will get a EO fundamental equal to 2 root 2 by pi into EDC, right? In that equation, we get 2 root 2 by pi into EDC by 2. So slightly change 2 root 2 by pi into EDC. You can find out with the help of same equations that is given in a single phase half bridge voltage source inverter. And this is nth harmonic, that is EO fundamental divided by N. Okay, so equation for this is same as like this, just the value is changing, but the procedure is same. Okay, so this is about the circuit analysis of this particular single phase full bridge inverter, or you can say single phase full bridge voltage source inverter. Okay, because again here it's a voltage source EDC, so it is a source in voltage source inverter, right? So if you have any doubt in this particular circuit, you can ask me. Otherwise, during this particular time, you can give your attendance. So start to give your attendance in a chat box immediately, just 1 minute. So time remaining for lecture is 8 minutes. So at 7 minutes, after 7 minutes, so I'll never accept your attendance. So start to give your attendance immediately, fast. Don't leave the class. The class is continuous after this attendance. Okay, so one more thing I want to tell you. Uh, Before 1 minute, total students are 66, but now attendance is given by 72. So don't think that the you may give attendance of your friends, so it may be accepted, right? Now at this time, total 68 students are connected, but attendance given by 72. So I'll just take a snapshot, and I already taken a snapshot at the 32 minutes, and again I'll take a snapshot at the end of meeting. So I'll compare this attendance with that attendance, and then uh, those who have not attended the lecture but given attendance, I'll just personally call them. So that it is very bad thing that the attendance is given but the students are not attending the lecture. So it is not for me. I already know that whatever the power electronic subjects and syllabus. So it is for you people. But if you behave like this is a very bad thing. Total 73 students have given attendance, but actually only 66 students was present at the time of lecture. Okay, no problem. So I'll just take a snapshot of your attendance, and then I'll compare your attendance with the present students and maybe attendance given by other students. So your name is also flashed there with a different roll number. So this is again a very, very bad thing. Okay. Is there any doubt in this particular circuit? Otherwise, I'll explain for the inductive load. Yes. Start. Can I start inductive load? Working with inductive load. If there is a no doubt in this resistive load, or maybe a single phase, full bridge voltage source inverter for R load. If there is a no doubt, then we will go. Okay. So again, due to poor internet connectivity, the connection may be lost, but a very short time is remaining. So still I'll start to explain with inductive load, right? So now we consider that this load is an inductive load, right? Inductive load, it means it's a RL load. Okay. Maybe a 1 or 2 minute is remaining. So automatically our connection may be lost after 1 or 2 minute. Okay. A very less time is remaining. So for inductive load, the circuit is again same, but this time the diode D1, D2, D3 and D4 is required. Otherwise your circuit output current is a discontinuous. So if current is discontinuous, then automatically your appliances, whatever the appliances you are using on this inverter, that may turns off, right? So these diodes are necessary for inductive load. So S1, S2, S3, S4 and diode D1, D3, D4 and D5. Total 8 devices are used. Diodes are also a power diodes, and S1, S2, S3, S4 are the power switches. Okay. So power switch means again a power BJT, power MOSFET, IGBT or SCR, right? For high power rating, SCRs are required, but for middle, low and middle power. So if your power rating is greater than 5 kVA, then definitely SCRs are required. But up to the power 5 kVA, you can use maybe a high power MOSFET, high power IGBTs, or maybe even BJTs. But BJTs are not used for high power rating because the BJT is basically thermal runaway is present in a BJT. So at high power, your device heats more. So once device heats, then thermal runaway may occur in a device. So power BJTs are not used maybe greater than 1 kVA, but you can use power MOSFET or IGBT so that for low power application or for medium power application. So up to the 1 kVA, you can use BJT, power BJT, but power MOSFET, IGBT or other power devices, you can use up to the